And it's my pleasure to welcome today Etienne Miquey from ENS Lyon, but soon to be in Marseille because he got a permanent position there. Congratulations. He will speak about evidence frames, a unifying framework, broadening realizability models. So thank you for agreeing to speak today, Etienne. You can go on.
Thanks, and thanks for
Oh,
the...
I will need to mute you before, actually.
Okay, mute me. And this should be okay. So again, thanks for the invitation. And indeed, I will present a joint work with Jeroen Cohen and Ross Tate about evidence frame, which is a structure we came with in order to reason about realizability models and define realizability model accounting for effectful computations. So to give you a bit of context as an introduction, you may already know that realizability can be seen as a technique to define models for a wide range of theories, in which instead of interpreting formulas by an element of a Boolean algebra, as it's usual in Tarski's model, you rather interpret formulas by a set of programs, which are called the realizers, and whose computational behavior is somehow dictated by the formulas they are interpreting. And besides defining models, realizability is also a very powerful tool in order to analyze the computational behavior of programs. And in particular, it allows us to extract computational information from logical information, in particular from typing properties of programs. We get a way to extract strong computational properties. Technically speaking, realizability interpretation is usually defined in 3 steps. So on one side, you have a language of formulas. On the other hand, you have a computational system, which is might be a combinatorial algebra, the lambda calculus, or something else. And then the interpretation itself, which is connecting the logical part and the computational part, is just the definition of the truth values for all the formulas. And the key ideas, and I will come back to that later, is that realizer computes, and that's through the computations, they somehow defend the validity of the corresponding formula. So you can see them somehow as players defending the validity of a formula in a game. And there is a notion of soundness of the truth value with respect to computation that can be seen as something which is usual in game. That is, if a term is reducing to a successful player, that is a realizer, then the original term is also a successful realizer. So that's what we call the saturation property. Algebraically speaking, when we deal with realizability as models, so we say that a formula is valid in the corresponding model if it has a realizer. And this can be seen as a particular case of a topos. And topos is the usual notion in category to deal with a wide range of models. And it was shown in particular in Andrew Spitz's PhD that all the toposes coming from realizability can rather be defined as coming from a notion that he called the tripos, which is a functor with certain properties. And I will also get back to this later. And then from the tripos, there is a uniform construction called the tripos to topos construction, which allows to get back to toposes or topoi. And usually in the computational system is defined as a PCA or the lambda calculus, which you can see as a set of codes with a partial application and some completeness property to get at least the pure lambda calculus. And in that picture, two things that were missing is that when you're in the computational system, you don't have any logical information about the model, while at the level of triposes, all the notions that has to do with computations and realizer, they are gone. So something was missing to connect the logical part and the computational part of realizability interpretation. And that was precisely the first goal we had when defining evidence frame. That is to get somehow an intermediate structure in between PCA and triposes that still have the information, the computational information coming from the PCA, and that already has the logical information of the model. And something very important that we have to say about this is that when defining a realizability model, obviously, since formulas are interpreted by terms, the notion of computations we pick is very important. And in particular, if we add some new effects, like side effects in the computational system, we might be able to get some new reasoning principles. So in particular, it's well known that we can get, for instance, Markov's principle out of exceptions, classical logic from control operators. And also what's interesting is that for one given reasoning principle, you can have several computational interpretations. So for instance, for dependent choice, you can use memoization or bar recursion and something which is very different, which is a quote function to get it. And from one similar side effect, so for instance, monotonic memory, you can get different reasoning principles. So for instance, Cohen's forcing or non-standard analysis. But in our case, when we look at PCAs, so the structure which is usually regarded as the base for intuitionistic realizability, it can only support one effect, which is non-termination. So nothing in that slide. And that was actually our second goal when defining evidence frame, that is to provide with a structure that has a way to smoothly integrate a lot of useful computational effects. And that's the two goals we will have all along this talk, to see how to define such a structure that is really connecting the computational information and the logical information of realizability models, and that also have a way to integrate computational effects. So to give a bit more of details on how usual realizability interpretations are defined and how they are regarded algebraically, we said that it's usually a three-steps recipe. So we have the formulas, the computational system, and then the interpretation connecting both. And the results that says that the interpretation is correct is usually called the adequacy lemma or the adequacy theorem, which says that out of a proof from a formula, so a proof in the logical system, you can extract a realizer that is a term in the computational system, which is indeed a realizer of the corresponding formula. And in the next slide, I will give you a very simple and usual interpretation starting from the lambda calculus and second order logic. So just to get a few idea on how to define a realizability interpretation, assume you have as a type system something for second order arithmetic. So you have first order expressions with arithmetical functions. Then you have connectives to get propositional logic. So for instance, implication, conjunction, disjunction, whatever you want. Then first order and second order quantifications. And on the sides of terms, you take the lambda calculus extended with recursion, the natural numbers, and so on, and consider it typed with the expected typing rules in second order logic for it. So you say, for instance, that 0 is the natural number of type 0, that the recursion has as type the recursion principle for natural numbers, and the usual typing rule for the lambda calculus. Then assume that for that system, you have the usual reduction rules. So the beta reduction, reduction for the recursion, and so on. How do we define a realizability interpretation for that system? Well, it's usually done by induction on the structure of formulas. And I would like to emphasize a few things here to highlight how the intuitions that I was giving before on realizability interpretation can be seen here. So for instance, I said that realizers, they are really terms performing computation. And one case where we see it is that the realizer for the implication, so a term realizing A implies B, is a term which is going to be waiting for a realizer of A to compute a realizer of B. And here also we can see that a realizer is really defending the validity of the corresponding formula. So how would you defend the fact that A implies B holds? Well, you have to be given something witnessing the fact that the premise A is holding. So that's really here the argument that T is waiting for. And then you have to return something which is a successful player for the conclusion that is for in the truth value of B here. If you, so there is a question apparently.
Yes, there is a question by Tom Hirschowitz.
Yes, thank you, and sorry for interrupting. I was wondering whether you would agree with this. You said that the usual framework for realizability doesn't take effects into account.
Yes.
But looking at your slides, your example now, maybe it doesn't also take exotic logical operations into account, like the polymorphic, like the second order quantification you have there?
Yes, well, in some sense, yes, but it's not hard to get it in the same setting. So for instance, here I'm taking a usual set of terms, and it's easy to get something that is polymorphic. So I wouldn't say that this is a hard thing to get in a realizability interpretation, but maybe for more exotic things at the level of formulas, I wouldn't be able to get it either.
Okay, thanks.
Okay. So I was saying that realizers are defending the validity of the corresponding formula. And for instance, if you look at the interpretation of quantifier, a term is a successful player, if you want, for all xa, if it is a player, a realizer in the intersection of all the possible interpretation of x by a natural number. So to be a realizer for all xa, you have to be a realizer for any possible instantiation of x by a natural number. And similarly for the second order case. And since, as we said, we want truth value to be saturated, we interpret the polymorphic things, so the second order quantifier, by predicate function that takes value into that returns as value saturated sets, so something that has the shape of a truth value. So that's the trick, which is usual. It's the same thing if you look at, I don't know, reducibility candidates or that kind of things. Okay, so that's the usual definition of a realizability interpretation. And to get a model, you just say that A is going to be validated if you have a realizer. As I said, this corresponds to a topos. And that was the picture before, the usual picture that many people have in mind. So you start from the PCA, the lambda calculus, and algebraically you can define a tripos. And from the tripos, you get a topos, which is the model. And people so far were, let's say, reasoning at the level of triposes rather than at the level of toposes when it comes to realizability, because everything is uniform afterwards. So it's enough somehow to consider the tripos to see interesting things. So what is a tripos? A tripos is a pretty complex structure, I would say, even though in the sense that it's very algebraic as a definition. So it doesn't really look like anything that has to do with the realizability interpretation I was presenting before. But let me give you a few intuitions on how it works. And I hope you will get convinced that it's really disconnected from the definition I had before and that it's also somehow complex. So a tripos is a functor which take a set and return a hating or a pre-hating algebra. So intuitively, you can see the image of a set as a predicate over that set. And the fact that it's a functor means that you know how to compose the predicates with substitutions, meaning if you have a function going to one context gamma to another context gamma prime, you know how to pre-compose somehow the predicates in gamma to get something in gamma prime. It also have, oops, sorry, it's the wrong direction. It also have to have quantifiers, and quantifiers, they are given by means of the existence of adjoints left and right to any substitutions. And here the intuition is that if you look, for instance, at the existential quantifier, it's taking somehow a predicate ranging over gamma times x, and it will return a predicate ranging over gamma, where the abstract variable x, the bounded variable x, is of type x. And therefore, it can be seen as a left adjoint to the projection going from gamma times x to x. And if you look at the equation you have to satisfy to be left adjoint to the projection, it's exactly the logical property of the existential quantifier. So it's nothing more than this, but categorically speaking, it has to be expressed by means of the existence of an adjoint. Then there is a condition saying, which is called the Beck-Chevalier condition, saying that you have the commutation of the quantifier with the substitution. And again, intuitively, it's rather simple. You just want to have the commutation, and categorically speaking, you have to express it by means of a commutation on any pullback and so on. And the last thing is the existence, and it's very important, of what is called a generic predicates, which means you have a distinguished set of proposition, and you have in the image of the set of proposition a predicate, a generic predicate, which is called holds. And this allows you to internalize in the tripos, in the set of proposition, the truth values and the predicates. So this is thanks to this that triposes define model not only for first order logic, but for higher order logic. So that's the definition of a tripos. And if you want a standard example, if you take a hating algebra, you can define a tripos simply by saying that you map any set to the function from this set to the hating algebra. You define the image of functions between sets by the precomposition. So that's really the intuition I was giving for composing substitutions with predicates. Then quantifiers are given by arbitrary mits and join in the hating algebra, and the compatibility just works. And the set of proposition is the hating algebra itself, and the generic predicates is just the identity function. So it's a heavy structure, but in the case of a hating algebra or something like this, it's kind of easy to define the corresponding tripos. So far so good in the sense that we had something that was suitable to define model of higher order logic in the case of realizability interpretation, but it's kind of a heavy structure. And also, and I hope it's clear that in the definition I gave you, there is nothing at all that reflects realizability in the sense that there is nothing about terms or the computational system and nothing about the realizability interpretation. And recently, at almost 10 years ago, after the discovery by Krivine that realizability could be reformulated to take into account classical logic, there was a work by Thomas Streicher to show that classical realizability can also be interpreted in terms of triposes. And after this, Alexandre Miquey came with a new structure, which is very simple and minimal, that has the benefits of taking into account all the computational system, the usual computational system, let's say, that were taken into account before with triposes, but also classical realizability. And that is complete with respect to triposes in the sense that any tripos can be seen as induced by an implicative algebra, and from any implicative algebra, you can induce a tripos. So that was somehow already a structure coming in between the computational systems and the triposes. And let's take a look at how it is. So an implicative algebra is a complete lattice to which you had a binary operation, which is somehow representing the implication, and a set, which is the separator, which somehow plays the role of a filter. So if you want, it distinguishes the set of valid elements in the algebra. And what is nice in such a structure is that even though it's really minimal, you already have a way to interpret system F, because you can interpret the second order quantifier by the mit and the implication by the arrow here. But you also have a way to interpret the pure lambda calculus. So you can redefine the application and the abstraction only using the arrows and the quantifiers, the mit. And if you want more detail on this, you can look at Alexandre Miquey's paper. I have a complete coq formalization also of this on GitLab and on my webpage. But what is particularly new in this structure is that you interpret types, as I was saying, but also programs in the same structure. So from a Curie Award perspective, it means you have something in which types and programs are the same things. And because of this, when you look at the order relation on the complete lattice, it has a different meaning depending on whether you're considering two formulas, two terms, or a term and a formula. If you have two formulas, it means that A is lower than B if it's a subtype. But if you take a term T and you have the information that it's lower than a formula A, it means that it's realizing the formula A. So somehow it tells you that the term contains more information than the formula itself. And if you consider two terms, it just means that one is more defined than the other one. And these interpretations, they are sound with respect both to typing, in the sense that if T is of type A, its interpretation is going to be lower than the interpretation of its type. And that's what corresponds to the adequacy property. You have more information in the realizer than in the the corresponding realized formula. And it's sound also with respect to computation, in the sense that if T reduces to U, then T contains more information to U. It's usual if you think, for instance, to 2 plus 2, it contains more information than 4. Okay, so that was about the computational part of implicative algebra. And about the logical parts, you can define an internal logic which reflects the usual realizability interpretation, in the sense that you say that A entails B with respect to the separator if the arrow A to B belongs to the separator, which means there is a realizer for A implies B in the separator. And you can redefine the connectives using the usual impredicative encodings for instance, the product, the sum, the quantifiers, and so on. And then you have that the entailment here for the internal logic is satisfying the usual adjunction property for the implication and the conjunction that you have in Hating algebras. So having this property, it's pretty easy to get a Hating algebra out of an implicative algebra by quotienting everything by disentailment relation. And then you know how to define a tripos, okay? And the construction is pretty similar to the construction for Hating algebra. So that was the picture before our work somehow. So there was this new structure called implicative algebras, which is very minimal, but maybe also too minimal, in the sense that since we interpret realizers and formula in the same set, if you change the notions of formulas or the notion of terms, then it's not clear that you still know how to encode it into an implicative algebra. In particular, if you consider some of the effects I will talk about later, we don't really know how to include them directly in an implicative algebra. Also, we have triposes, but as we said, everything in the definition of a tripos is logical, so it doesn't really account for realizers, terms, or computation. And all this is still lacking of a way to incorporate effectful settings in the pictures. So in short, the message here is that we had two very general structures to deal about realizability, but none is really accounting for realizers, or at least not for something which is not fixed, as in the case of implicative algebras. And that's where evidence frame appears. So how is it defined? It's very simple. It's exactly as in the recipe I was giving before. You have three things: a set of propositions, a set of evidences, and a realizability relation connecting evidences and proposition. And the main thing to keep in mind is that the definition, which I will give in the next slide, has to be seen as a minimal specification on the structure to get a realizability interpretation. By specification, I mean it's just condition that something has to satisfy to define a realizability interpretation, and nothing dealing with the precise implementation. So in particular, as you will see, there is no assumption on the computations of evidences, for instance. So how is defined an evidence frame? We actually only ask for evidences and proposition to present a minimal structure to have an interpretation of logic. So we want to have a proof of reflexivity, that is some evidence that phi entails phi. We want evidences to have a way to compose evidences. So we want to be able to compose one evidence from phi1 to phi2 and another one from phi2 to phi3 to get something from phi1 to phi3. And for the logical parts, we want to have something in the proposition that represent the maximal elements, that is an element which we call top and a proof that anything entails top. We want something that represents the conjunction and something that somehow behaves like pairs and projection, in the sense that we have a way to get from the conjunction of phi1 and phi2 to phi1 or to phi2, and to compact two proofs from phi to phi1 and from phi to phi2 to get a proof from phi to the conjunction of it. But it's only, again, a specification here. If you look at it, there is no assumption on the way what we call the pair here and the projections behave together. So there is nothing saying, for instance, that the projection of a pair is returning the first or the second component. Okay, it's just we want to have enough structure to express something that satisfies this. And the last requirement is compacting what we want for the implication and the universal quantification. So it's something that takes one proposition on the left-hand side and several propositions on the right-hand side. And that comes together with something playing the role of the abstraction and the evaluation function. And again, this is just the usual requirement we would have to get the modus ponens and the introduction of the implication. Okay, and that's it. So I might be insisting a lot, but it's really easy, and it's really just a minimal specification on the structure we need to define a realizability interpretation. But many things might enter in the picture, so we don't say anything about the precise notion of terms or computation we want, and that's why it will be so useful afterwards. So let's get back. Okay, new question.
Yes, new question by Tom.
Yes, thank you. That was a bit fast.
Yes.
The universal implication is a bit hard to read. Could you go over it again, please,
Yes.
a bit more slowly?
So assume you have it's A on the left-hand side and the set of B1, B2, and so on the right-hand side. And the implication from A to the set of B's is somehow behaving like something which goes from A to any possible B. So in particular, if you look, I don't know, for instance, at the second rule, if you have the implication, this implication, and something that validates the premise, then by evaluation, you can reach any possible conclusion. And to perform the opposite, that is the introduction of the error, you need to be able to go from any possible conclusion to the error.
Okay, so I see if there wasn't this vector
yes,
notation, it would be just the two usual rules for
yes, and if you forget about the premise, it's just the usual rule for the universal quantification.
It combines the two. So you mean that the presence of the vector is supposed to model for all?
Yes.
So it's like a 2-in-1.
Yes.
Okay.
If you put top instead of phi 2 here and there, you really only get the universal quantification.
I see. Thank you. Sorry for being slow.
No, that's okay. And we could have defined both separately, but because for many reasons, and in particular, we formalized all the proof and so on, it was easier to have one compact definition.
I see. Thank you.
Okay, so Etienne, we have another question in the chat by Paul Taylor, who says, it's a bit unclear with the proposition there, but what is the algebraic structure on the evidence terms?
There is no assumption.
I can't hear you.
Oh, is that better? Yes?
A bit.
Okay. So that might be too loud, but at least you hear
great.
me. Okay. So there is no assumption on the structure of evidences besides the fact that you have this function for pairs, this function which is representing the lambda, and the existence of some distinguished codes, which are the first and second projection, the evaluation, top, and so on. So here there is absolutely nothing else as assumption on evidences. And as we will see in a minute, when we want to define an evidence frame from a PCA, the codes we pick for all this are really the expected ones. But if we want to consider something more exotic or something with effects and so on, we will be able to also define evidences as these sets, because they will just enter in that picture. It's a very weak axiomatic we have on evidences.
We also have a remark by Gabriel Scherer. From a distance, this looks like a Cartesian closed category without any equalities, without the quantification part on the right of implication.
I'm not a specialist enough on CCC, but it might be the case. But a very important point here is that, in fact, indeed, we don't have any equation, we don't have any equalities. So We don't have anything that says how the computations should be defined. And that's very, very important.
Okay, I think you can go on.
Great. Okay, so back to the two goals I was mentioning before. With this, I first have to show you that indeed we have an intermediate structure which is in between PCAs and triposes. And to go from PCA to an evidence frame, it's pretty easy. So if you take as a definition of a PCA a set of codes that has a partial application and an extension to expressions with free variables, such that you have an assignment to expressions with free variables to codes, which satisfies what should be satisfied by the pure lambda calculus. So that's what we call the functional completeness requirement. But you can take a definition with K, S, and the application if you prefer. Well, from this, to define an evidence frame, you just do what you would do when defining a realizability interpretation. That is, the set of proposition is defined as the power set of codes. That is, a proposition is just the set of its realizers. Then an evidence is just a code. And to say that an evidence realizes the entailment from phi1 to phi2, you require that for any possible code in phi1, you want the application from E to E1 to terminate and to reduce to a code E2 which belongs to the conclusion, okay? And then you define the connectives and their evidences, so in particular the pairs, the projection, and so on, just like you would do in a usual realizability model. Nothing surprising here, and it works. The other side of that goal is to show that we know how to go from evidence frame to triposes. And again, it's pretty easy in the sense that given an evidence frame, we have a construction which we call of uniform families that allows us to define a tripos. And it's very similar to what we had before with implicative algebras or with hating algebras, in the sense that we first define an ordering relation on predicates. And we say that phi is lower than phi prime if there exists an evidence that uniformly relies phi to phi prime, meaning it's a valid realizer for any possible instantiation of the variable in phi and phi prime. So that's the usual uniform entailment relation that is defined in realizability. And then to get the structure of a hating pre-algebra, we do it pointwise with the structure we have in the set of propositions. So we have the conjunction and so on. And then the rest of the definition is as usual. So the substitution is mapped to the precomposition of functions. The quantifiers are defined by preimages, and the generic predicate is again defined just by the set of proposition is the set of proposition is in the evidence frame, and the generic predicates is just the identity function. So nothing very surprising, and for people familiar with realizability interpretation, that's when you want to define a tripos, it's exactly what you do, except that instead of having an abstract notion of proposition and an abstract notion of evidences, you have a particular implementation at hand, usually. Okay, so that was for the first goal. For the second one, I want to show you how we can incorporate useful computational effects in that structure. And let me just refine the notion of PCA to define what we call the computational system. So again, assume that you have a set of code, assume that you have a partial application, and now we want to extend it with a set of states, which we write sigma, that is equipped with a possible future pre-order relation. So we have a way to say that a state is a possible future to another one. And then we have to extend the definition of the reduction relation and termination relations to take into account the states. So the definitions are really standard. We can look at one if you want. So for instance, to see the definition of the reduction here. So we say that the application of an expression to another one in the set sigma is going to reduce if we can reduce the left expression in a new state to a code, the right expression in that new state to another code, then the application of the two codes in the last produced states in a third state to get a result. And we say that it successfully reduces in that new state to that result. So it's nothing very surprising. We just have to wire the fact everywhere that we have a state and that the state evolves along the computations. And then we also rephrased the functional completeness requirement to take into account the states. But again, it just means that we have enough structure in the expressions and codes to get the pure lambda calculus. And we had one requirement, which we call preservation, that says that if something reduces, then the state it reduces to has to be a possible future of the original one. So just something to say that the pre-order relation is really reflecting the something about the possible futures, or that the reduction is sound somehow with that relation. Okay, and with just that definition, we have a way to incorporate several effects. So if we want to get back to a PCA, we only have to take as a set of states a singleton, and that's the exact same definition. It collapses to the definition of a PCA. If we want to take into account non-determinism, we just have to add to the set of codes a particular code we can call flip here, which is always terminating and which reducing either to the first projection or to true and the code representing the Boolean true, or to the code representing the Boolean false. Okay, you can think of it as just you flip a coin, and then you get non-determinism. You can have mutable states. So here you really use the set of states technically you say that the set of states is just defined as finite partial maps from natural number to code. So you have a memory if you want. You define the ordering relation between states as an inclusion. So by representing an extension, a strict extension of the memory. And you take a set of codes, the usual set of codes, plus a lookup function, which allow you to look in the memory to check whether something is already defined, in which case you access to the value in the state. Or if it's not defined, then you extend the states to add this new element. Okay, so this also enters in what we call the computational system. And the last example we have in the paper is by extending the system with an operator which we call fail, which is always terminating but never reducing. So it's something that always terminates, but you cannot get any value out of the computation. Then it's kind of the same idea if you want to define an evidence frame, in the sense that you define propositions as set of codes, but since we have states, we have to take into account code together with the states. And we want this proposition to be future stable, in the sense that if a code is somehow valid together with the states, then for any possible future of that states, you want it to be valid also. Then you take as evidences the set of codes, and you define the implication just like we did before. But this is almost true. There is two subtleties we have to take into account. The first one is we want to only consider what we call valid codes. That is, we don't want to have codes just like fail we had before that are never reducing. And to that end, we can define what we call a separator, which plays the same role as in implicative algebras. So it has to be a functionally complete subset of C, meaning we have, again, a functional completeness requirement satisfied, and it has to be closed under reduction, plus a new requirement, which we call progress, which says that if something is terminating, then it has to reduce, okay? So fail is precisely an example of a code which is not satisfying progress. But if progress holds for all codes, which is the case if in the first example I was giving, then you can take as separator the set of all codes, or you can also define separator from functional completeness from a subset of codes which satisfy progress. Okay, so that's one thing. And the other one is that we have to choose the way we interpret non-determinism. In the case we have non-determinism, that is, we have to say whether we want the reduction property to be satisfied in all possible cases, which is the demonic interpretation of non-determinism, or only in one possible case, which is the angelic interpretation, that is in the interpretation of the implication here of the realizability relation. We have to decide whether it might be the case that it reduces always or at least once to a successful realizer. Okay, and having a computational system, a separator, and an interpretation of non-determinism, we define an evidence frame really as I was saying. So the set of proposition is the set of future stable stateful predicates. So in the Bohr sets of the sigma times the set of codes, but such that it's future stable. Evidences are defined as codes, and the realizability relation is defined using the interpretation of non-determinism. Okay, so that's almost the same definition we had before, just it takes into account states, non-determinism, failure, and many more things. And since we have, I have to insist on this, since we have an evidence frame, the very same construction gives us a tripos. And that's a uniform construction. So in all the cases of all these effects, we have the same construction for a tripos. Okay, so it's really emphasizes the fact that we can, if we want to reason about the model, it's enough to reason within the evidence frame to see what we will get in the tripos, since it will always be the same construction, regardless of the effects and the evidences we choose. And one example I would like to give you, which is which was at the root of this work. It's a paper before by Lyon, Rostet, and somebody else, students they had. So in that paper, they showed how a realizability model induced by a PCA always models the countable choice principle. And in our setting, it means that the construction, the uniform family construction applied to the evidence frame taken from a PCA validates the countable choice. Then they showed how adding non-determinism makes it negate the countable choice, but adding states and memoization, so something we know how to do with the computational system, we get back the countable choice principle. And not only do we have a way to express this here in our setting, in the language of evidence frame, but more than that, here, all the statement I'm giving here in blue, there are only specifications on the models. So they are not saying anything in the particular implementation that we have to choose. It's just say for any possible set of terms and any possible logical system in which we have enough structure to get flip and lookup. So it might be a very different systems. We know that we always will get these theorems and these results. So that's a very strong result in the sense that it's no longer applies to one particular system, but to any possible system that satisfies the specification. So that's one of the interests of reasoning within evidence frame rather than directly in one particular implementation. And before going to my conclusion, I would like to tell you a bit more about what we have in the paper. So to complete the picture about the relation with implicative algebras and triposes, we have a way to construct an evidence frame out of an implicative algebra. And the definition is kind of natural when we know both structure, in the sense that we take as proposition the whole algebra, and we take as evidences the separator, just like we did before. And the realizability interpretation is just defined as the evidence is lower than the implication. So this is how we express realizability within implicative algebra. So it's natural. And then the rest of the proofs are just like for defining the internal logic of implicative algebra, and it works. But what is particularly interesting here is that we can see that this definition is somehow erasing the differences between evidences and propositions, in the sense that both proposition and evidences, they are in the same sets. So it works because we come from an encoding of lambda terms and so on, but we are blurring the distinction between both. So we have, in general, more information in evidence frame. And also we can see that the triposes we get from an implicative algebra are going through an evidence frame are equivalent. So it's really the same construction. That's one thing. And you may remember that we also had, Alexandre Miquel had some completeness result for implicative algebras, and we have something similar here. So we know how to define an implicative algebra, and I don't want to enter into the details of that construction here. But the trick to go from an evidence frame to an implicative algebra is somehow the same that Alexandre was using to start from a tripos. And what's interesting here is that if we do the round trip from evidence frame to implicative algebra and then to evidence frame again, we get something which is equivalent to the original evidence frame. So we really have somehow the same thing through the loops, but and for people interested in this, it's only extensional. We also have a completeness result with respect to triposes. So there is some kind of magic trick, which is in the paper. And as a good, I wasn't the magician, it's Ross, but I won't show you the trick here. But we have a way to define also an evidence frame from a tripos. And the construction works for any tripos that has somehow a construction to reflect external truth. So it's a very loose assumption in the sense that it's valid for any set-based tripos or any tripos that satisfy the axiom of choice or many things. So we express it like this because it's the minimal assumption we found to define the construction. And when we look at the construction here, we have the set of proposition, which is the set of proposition of the tripos. And the set of evidences is a subset somehow of the relation and proposition. So we can see that we don't have any computational information. We somehow have lost the notion of evidences once we reach the tripos. But again, we have a way to show that if we do the round trip from triposes to evidence frame and back to triposes, or starting from evidence frame, that we get something that is equivalent, and we have actually a bi-adjoint, bi-equivalence relation between the two constructions to go from triposes to evidence frame and the converse. So that would be the final picture. So we have something which is in between implicative algebras and tripos, which has much more information than triposes in the sense that we have evidences. We have a notion of terms. We have something which is more flexible than implicative algebras because we know how to incorporate a lot of effects. And if I had to highlight only one takeaway message for this is that triposes, which was regarded as the good place to reason about realizability before, is somehow an evidence frame that has forgotten about its evidence. And therefore, there is much more information in evidence frame. It's easier to manipulate evidence frame. So there is no reason to continue working at the level of triposes if we want to deal with realizability, because everything we do at that level, we can do at the level of evidence frame, and it's more flexible, easier to do, and so on. Also, all the constructions you have on that picture, at least for the completeness construction, we have formalized them in Coq, so it's available, for instance, on my webpage if you want to take a look at it. So to conclude, I showed you how we define an algebraic structure which we call the evidence frame that accounts for realizability model, but it's not only one new algebraic structure, it's a structure which is particularly flexible in that it takes into account several effects. It's uniform in the sense that we know how to define a tripos and then a model in a uniform way from that structure. And it's complete with respect to what was existing before, whether it be the triposes or the implicative algebras. For our next papers, we would like to use this structure to reason collectively about the models. And just like in the example I presented you before about countable choice, it was a result dealing with any possible model satisfying the specification given. evidence frame allows us to get results, to express results that says that any evidence frame that satisfies something on its structure, something on its meta theory, and so on, will models a particular principle. So we have a way to reason on all the models that are going to satisfy some specification. So that's a very convenient tool in that regards. Also, we would like to study robust implementations. By robust, I mean implementations that doesn't have to do with a particular implementation, but with the, and I will take the question just afterwards because I'm finished. Or implementations that are valid as soon as a specification on the implementation is okay. And in particular, there is a hierarchy of choice principle that has been defined by Hugo Herbelin and Nouria Brede. And we would like to see whether we can get results similar to the one that exists for countable choice for some other principle in their hierarchy. And in the paper, we have a notion of morphism for evidence frame, implicative algebras, and triposes, and we would like to study them further. And one last thing we would like to do is to be able, thanks to evidence frame, to express in a very general way the consequence that a given effect may have on the resulting realizability interpretations. So for instance, there are results saying that if you include a fork, something which is very non-deterministic, we have a collapse of the structure of the realizability interpretation to a structure of a usual forcing model. And we would like to be able to have that kind of results for different effects, but always reasoning on a generic setting and not in a particular implementation. So that's all I wanted to present you, and I will be welcoming any question, and I think that I already have one.
So thank you very much, Etienne. Actually, you have one question in the chat by Gabriel and another by Paul. So let's start by Paul.
I can't seem to get my video, but anyway, no, I just wanted to say congratulations on a very sophisticated piece of work. It's a pity that Andy Pitts and Martin Hyland and Peter Johnson are not here to see it.
Indeed.
Did you hear me?
Yes. Yes, I can.
Right. Okay. So I was just wondering. I mean, when you have something as sophisticated as this,
Yeah.
Connected to other very sophisticated pieces of work, sometimes it's very difficult to fit them all into your head at the same time, and as it were, get the punchline. So I was wondering whether you could say something very briefly about going from one end to the other. If you have something, some nasty computational effect at one end, what does it do to the topos at the other end of the construction?
Oh, so the point is that here, everything that has to do with computation, you can observe it at the level of evidence frame. But once you get to the tripos or the topos, everything that has to do with computation is somehow hidden.
All right.
So, the only thing you will be able to see is whether something is valid in the model, some logical principle is valid in the model, but you no longer have any access to the information of why this is valid and what was the realizers and how the computation have anything to do with the validity of a given principle. So that's, at least in our opinion, one of the very strong points for reasoning in evidence frame rather than in triposes when we want to deal with realizers precisely in computations.
Okay, so suppose somebody's interested in the topos end of it. So I'm imagining I might be Wesley Poir building his synthetic domain theory on top of the effective topos.
Yeah.
So how what interesting things could you do to change that by putting in computational effects at the bottom end?
So if you only, so one thing that is clear, if you only want to, if you're only interested in the topos, you can compose go directly from evidence frame to toposes and forget totally about the tripos. Then so far we haven't looked at the consequences that our effect have at the level of toposes. So I don't have any nice example to tell you, oh, if you do this, you will get that in the topos. But there is no reason why we couldn't be able to do it. So for instance, what has been done for countable choice, it will be, you can apply it to say if you get the affected topos coming out of something with a state and some kind of non-determinism of control operator and so on, you know that you will still be able to have countable choice. But it will always refer to something, I guess, that has to do with computations. Now, what might be interesting would be to get example of effective topos in which some surprising principle is validated or not validated. And that could be the case insofar as we have interesting example of realizability models for instance, in classical realizability, in which, for instance, you don't have the continuum hypothesis or the axiom of choice, and that could enter in our picture, but we haven't looked at it yet.
Okay, well, congratulations again.
Thanks.
Thank you, Paul. So we have two questions in the chat. The first one is by Gabriel. Naive question. I understand that it's not clear how to add effects to implicative algebras, but could you use the completeness result to transpose your respectful EF into implicative algebra and see what you get?
So quick answer, of course you can. And when you look at the definition of the complete for the completeness results, you know that you don't want to do it because it's a particularly complex construction, and you go from you totally lose everything, like the cardinality exploded, and so it's really something you don't want to look at.
Okay, and there is another question by Tom Hirschowitz. Similar comment. It's hard to buy that a tripos is an EF that has forgotten its evidence, since you can recover it through the P equivalence. Is this missing the point?
So that's almost the same story, even though it's not as complex as the construction. But when you recover the evidences, the only thing you recover is some logical information about it, like start from an evidence frame, go to the tripos, and the only thing that you will see is what is realized. So you know that, I don't know, A implies B is realized, but you don't know by who and you don't know how. And when you will get back to the evidence frame, you somehow have something telling you, oh, I had at some point something in the shadow that was a realizer for the implication, but I don't have any information about it. So in particular, you have no information on how it computes, what it looks like as a term. And so, of course, you always have the logical information that it was realized, but you don't have anything else.
Okay, thank you. Are there other questions? Yes, one by Tom.
Yeah, if I may, I would like to react to your answer. So
Yep.
it seems that this biequivalence is kind of forgetting something after all. So maybe the answer lies in the notion of model between evidence frames that you have.
Ah, you mean the morphisms?
Yeah, it seems, from what you say, it seems that when you go around the equivalence, you kind of collapse. Like, for example, if you have several witnesses for some logical principle, several realizers, then in the evidence frame that you obtain by going through the equivalence, they will all be collapsed into one. Is this right?
I don't want to say something that is wrong because I don't have the I'm not clever enough to compute live and direct, but it might be the case. And yes, one thing that I can say is that all our notions of morphism, they are somehow tailored to say we preserve the basic structure of everything, and in the end, when we go through all these loops of completeness, we get equivalencies of triposes. So it might be the case that we could define, let's say, a weaker notion of morphism for implicative algebras or evidence frame that doesn't really induce through all the constructions some and equivalencies of triposes. But that could still be an interesting notion of morphism. I don't know, something that's, well, I have in mind other examples in a work that I had with a student about morphism for implicative algebras, something that only preserve, I don't know, the structure of hating algebras in the triposes and not the whole thing or that kind of stuff. And here, so what I want to say is that indeed we lose something, I think, doing that loop. And we consider the evidence frame to be the same in the sense that they validates in the end the same principle. That what it means, like when we look at the level of triposes, we have equivalent models. But the notion of equivalence within of morphism within equivalent evidence frame doesn't say anything about the structure of evidences, the structure of proposition, and so on.
Okay.
It's especially about evidences. It just say you know how to relate the fact that something is realized, rather than we know that we have the same realizers.
So and so then,
yeah.
Could you speculate on what you would get if you switch to such a finer notion of morphism between evidence frames? What would happen to the other bioequivalence?
I have really no idea, and I could cheat and say that I just saw that Lyon is also listening. So if she had, if she had a better idea, but well, I don't know. So far, okay. I don't know.
Never mind.
I'm sorry, I am here, but I'm with my baby, so I missed that last part of the question.
Okay.
Do you want to repeat it?
Yeah, I can try to summarize the discussion and repeat. So it seemed that the fact that you lose something going through the right hand by equivalence to triposes has to do with the notion of morphism between evidence frames being maybe too coarse. And so like losing information about how many evidences you have for some proposition and so on. And so I was asking, if you switch to a finer notion of morphism, which keeps track of evidences, what would happen to the other bioequivalence on the left?
That's actually a very good question, because we are still working on finding the right notion of morphism. But I don't suspect that to really affect the triposes that we get, because as Etienne mentioned, the set of realizers in the evidence frame actually collapses into just a propositional statement about the existence of a realizer. So even if we keep track of more information about that set of realizers, I don't anticipate that to have any effect, but I might be wrong here. We haven't worked that out.
But I suspect that this will break by equivalency. Well, maybe you will get an adjunction, but I was more asking about the other bioequivalence with implicative algebras.
I don't have the answer either, but I think something that has to be emphasized is that on the right-hand side, the biadjoint bioequivalence is intentional, while on the left-hand side, it's only extensional. So the nature of the evidences is already lost somehow. So I guess that whatever you do at the level of evidence frame to refine the notion of morphism, to get something more precise on the evidences and so on, will get lost somehow in the completeness construction with respect to implicative algebra, because it's only extensional.
Yeah, I don't know what that means. It means that you
don't look at the, it's like the equality is You have an extensional notion of equality. So
You mean in Coq, because you're implementing this in Coq?
in your meta theory, because yes, indeed, we in our meta theory we choose the weakest we could, and in particular we do it in type theory, and we really distinguish between the intentional and extensional notions. While, for instance, in all the work by Alexandre, everything is extensional.
Okay. Okay, thank you.
Yeah, thanks.
Thank you, Tom. Are there other questions? Okay, if there aren't, then thank you very much. I will stop the recording first.